Okay, I wanted to create a quick video here dealing with subspaces, vector spaces, and dimension. Okay, let's start out like this. Suppose U is a subspace of Rn. Okay, all right. Here's a quick question, and we want to start with, what is the maximum number of linearly independent vectors in U? Okay, does such a thing exist? In fact, yes, the answer is n or fewer, and I'm going to prove that by contradiction here. Okay, let's start like this. Suppose that k is greater than n, and that u1 through uk are linearly independent in my subspace, and therefore in what, Rn. Okay, then what would that mean? That would mean that the only solution to this vector equation, a sub 1 u1 plus a sub 2 u2 plus a sub k u sub k is the zero vector, is what? All the constants would have to be zero, right? A1 through ak would have to be zero. In other words, the only linear combination of u1 through uk which yields the zero vector would be what? The zero coefficients there, okay? But let's go ahead and see there's a problem with that. But if we go ahead and let u sub j have this sort of representation here, u1j, u2j, unj, all the way down here, okay? So this is some sort of what? Remember, it's an n vector, right? That's all I'm saying here, okay? So it's got a first element, a second element, and finally so forth down to an nth element. Okay, and this is going to be true for each of the vectors. J goes through from 1 through k, okay? Now we can write this equation right here as a following linear system then, okay, which I'm going to do here, okay? All right, so these are all the u's here representing what? The various vectors, okay, in our regular component form. And on the other side, we have what? The zero vector in component form, so zeros here, okay? But if you notice here, the rank of the matrix is at most what? N, right? The rank can be at most n here because that's the number of columns, okay? And if k is greater than n, then this homogeneous system, which would have to be what? Consistent, right? Remember, homogeneous systems always have what? Zeros over here. They're always consistent. Okay, you never get a contradiction there. But it would have k minus n, which is greater than zero, assumably, if k is greater than n, free parameters, and then you would have what? A non-unique solution, or in fact, solutions. Okay? All right. That would be a contradiction, right? Okay, because they were supposed to be, the question was about, they have to be what? Linearly independent. So k is going to have to be less than or equal to n. Okay, so my question again, okay, so if I have a subspace of Rn, okay, the number of possible linearly independent vectors I can pick from U is going to be what? N, or possibly even fewer, okay? Okay, now what I'm going to do is just say k is the maximum number of linearly independent vectors in my subspace U, and let B here be U1 through UK be such a set of vectors in U. Okay, so these are what? This is supposed to be a linearly independent set of vectors in my subspace U, okay, which is contained in Rn, right? So we know that k is less than or equal to n here. All right. But this is the maximum number that you can actually pick from U. Okay, so I'm assuming k is the maximum number, and this is such a set. Okay. Since subspaces are closed under linear combinations, remember that? Okay. It follows that the span of V, which is also going to be a subspace, right? Did you prove that, right? The span of any set of vectors actually forms a subspace in any vector space. Okay, but the span of these vectors is a subspace of U. In fact, I'm going to show that the span of these vectors is going to have to be U itself. Okay? Since if U contains some vector that was not in this span, okay, so let's assume that the span of U is smaller, or span of B is actually smaller than U itself, then if V contains some vector that was not in the span of B, then I could what? Just consider this set of vectors, U1 through UK, together with V, and that would form a linearly independent set of K plus 1 vectors in U. But that contradicts what? The maximality of K. We said K was the maximum number by assumption here. Okay? Okay? So that means if you've got what? A set of vectors, the most that you can pick within a subspace, right? And still be linearly independent, then the span of that thing is going to be the space itself. Okay? All right. Just a definition here. Okay? Since U is the span of B, okay? All right. Well, B is defined as was previously, and B is a linearly independent set, we call B a basis for the subspace U. Okay? All right. Let's talk about a little bit more what a basis would mean then. A basis for a vector space is a set of vectors that spans the space uniquely. What does that mean? Span the space uniquely. Okay? That is, every vector in the space can be represented as a linear combination of the basis vectors. So that's what it means. It spans the space, and the representation is unique. Okay? So it's got to span the space, but it's got to do it uniquely. Okay? So you can't have two different representations as a linear combination of basis vectors for the same vector. Okay? What are some examples of bases you've seen before? Okay? Well, this is a very easy common one here. In R cubed, I, J, K, so 1, 0, 0, 0, 1, 0, 0, 0, 1, respectively, is called a basis. Okay, this is sometimes called the standard basis. And you can extend this, by the way, to what? Rn. So that would be what? 1 with zeros, 0, 1, and then zeros, you know, and so forth down the line. So you could create this in R4, R5, R6, create the standard basis. 1 in one of the places, one of the rows, zeros everywhere else. And then you're actually going to have n of them in general. In this case, n is 3. We've got 3 standard basis vectors. Okay? Okay, this is actually a basis. Do you see if I take any vector ABC in R cubed here, I can write it as what? A linear combination of I, J, and K this way. That's A times I plus B times J plus C times K. And so there's it as a linear combination of I, J, K. And it's the only possible such representation, right? All right. Can you prove that to yourself? This is the only way to do it too. Okay, it doesn't take a whole lot of work there. Yep, this is the only way you're going to be able to do it. So this is actually going to be a basis. Notice this was completely arbitrary. So any vector ABC from R cubed, I can represent in a unique way as a linear combination of these guys. Okay? Okay, here's another example. You might try this for yourself. EFY, exercise for you. 1, 0, 0, 1, 1, 0, 1, 1, 1. This is another basis for R cubed. It's not a standard one by any means, but can you prove that this is a basis for R cubed? Okay, all right, just like this one is. It's not going to be easy for quite as easy for our formula for the coefficients, right? To get ABC here, but it's not too difficult either. It's something you should be able to do with Gaussian elimination. Okay, and in fact, let's just mention this and you'll see why this is true later here, just a minute. There are infinitely many bases. That's the plural of basis, is bases. Okay, I'm not responsible. That's not bases, that's bases. Okay, plural of basis for any vector space. So there's infinitely many bases for any vector space over R or C. There are finite fields, but that is not something we've talked about. So our vector spaces are always over the reals or complex numbers. Okay, all right. Speaking of the infinite here, by the way, let's throw this in here. There are vector spaces that require bases that are infinite. That is, no finite number of vectors is sufficient to span the space. They're not going to be the focus of the course, but we will mention them from time to time. Some of our function spaces that we were looked at in a previous video. We're going to be dealing overwhelmingly with just finite vector spaces. In other words, ones with finite bases. Okay. Here's a quick question here. Can a vector space with a finite basis, okay, maybe I'll put that in parentheses, have two bases with a different number of vectors? And the answer is no. Okay. Nope. If you've got a vector space with a finite basis, and you've got two bases, they always contain the same number of vectors, okay? No, the number of vectors in any basis is fixed and is called the dimension of the vector space. So dimension here, okay? So that's a fixed aspect of any vector space, including subspaces, right? All right, let's just try to give a proof of that statement here, okay? All right, it's sort of different formulation here than you might have seen before, but I think I have a pretty tight representation here. Suppose that base 1, or B1, V1, V2 through Vm, and basis 2, which I'm calling B2 here, W1, W2 to Wn, are both bases for the vector space V. Then I claim M must be equal to N, okay? So that's... you can't have different numbers of vectors in each basis, okay? So M and N have to be equal. All right, now I'm going to start out for my proof in the following way. Suppose or should I say, since B1 is a basis for V, the vector space, there exists a unique representation of each of the vectors in B2, right? Okay, because B2, all these vectors still lie within the vector space V also. Okay, so I wrote it this way. W, this should be I goes from 1 to N. Oops, typo there. Okay, Wi equals the summation, J goes from 1 to M, A sub I, J, V sub J, okay, and that should go for I goes from 1 to N. This is just saying, this is what? Just showing Wi, where I goes from 1 to N, is a linear combination of these vectors, okay? All right. Now let's go ahead and write this in a matrix form. This might make more sense to you here. So I wrote this in a matrix form. Okay, this is kind of a neat situation here. Okay, so I've got A11, A12, so forth down to A1M. Okay, let's look at this first row here. This is just saying it's A11 V1 plus A12 V2 and so on and so forth plus A1M VM equals what? W1. And then I do the same thing for the second vector here, W2 and so forth. So we've got what? M columns and we've got N rows. Okay. Now, the nice thing about this situation, we're not really used to having what? Vectors sticking in here or being up here. Okay. Just floating above. These are just, right. Those aren't really part of the matrix. They're just indicators. These are actually part of the matrix. These are vectors here. But this is an augmented matrix, and we're going to show here we can perform elementary row operations on this as usual, right? What? You know, linear combinations and stuff. We can do that with vectors. So this is actually going to work here. Okay, so this information is encapsulating that. Okay, all right. So keep that in mind here. Now, the way I've set this up, I've assumed that M is less than N without loss of generality. As you move on in your mathematical career, you will see woe log without loss of generality. Okay, I'm going to say M is less than N. I don't have to create two arguments here. I'm going to show you why. Okay, just real quickly here. If I have two bases here, right, and I'm supposing that one has more vectors than the other does, okay? Well, if that's true, that these don't contain the same number of vectors, there's got to be one of them that contains the smaller number of vectors, okay? And I'm calling that one what? M, this guy, okay? So I'm saying this is the one that has the smaller number of vectors. So I'm going to just say without loss of generality that M is less than N, okay? Now, I said I could perform elementary row operations on this thing like usual, which is what I imagine doing, and getting it down into what? An echelon form. Since the rank of the matrix is less than or equal to m, because it contains m columns here to the left of the dashed vertical line, and m is strictly less than n, to be consistent with more rows than column, remember n is greater than m, if this has more rows than columns, the only way it could be consistent is what? If I end up with rows, at least one row, and maybe more, rows at the bottom consisting entirely of zeros. And that would, to be consistent, that would mean I would have to get what on the other side? I would have to get the zero vector over on the other side. But wait a minute, what would that mean? That would mean this indicates that there's some sort of non-trivial, meaning just not multiplying everything by zero, there's some non-trivial linear combination of vectors from B2, right? When I perform these linear combination on this, somehow I got a zero vector down here, okay? Yielding zero. That would indicate that the vectors in B2 are not linearly independent. That's a contradiction. Why? Well, this was supposed to be a basis, right? A basis has to be what? Span the space and be what? Linearly independent. Well, this would indicate that they're not linearly independent. Okay? So the idea that m is less than n must be false, right? So they actually have to be equal. Alrighty? Well, I hope you understood all that stuff. We shall continue with another video.